You may recall from Calculus 1 that there is a section on differentials. The differentials are talking about small incremental changes in a variable and used in error analysis. So this section generalizes that concept to multiple variable functions, and we'll see if you can recall it from Calculus 1. If so,
Obi-Wan has taught you well.
And then so we'll move on and try to apply that same thing to functions of more than one variable. So from y equals f of x, you can extract the differential formula dy equals f prime of x dx. Maybe another way of saying that would be dy dx equals f prime of x. But similarly, if z is the function of x and y, we can represent delta z, the increment of z given incrementals delta x in x and delta y in y, as delta z equals f of x plus delta x, y plus delta y, minus f of x y. In other words, the slight change in z when x and y change by slight amounts also. So first, the definition of what's called the total differential, which is a computational device we'll use in the next example. So if z is a function of two variables and delta x, delta y are increments in those variables respectively, then the differentials of independent variables x and y are dx equals delta x and dy equals delta y. That's easy enough. And the total differential, here's what's really new, of the dependent variable z is dz equals the partial derivative of f with respect to x applied to x and y, or at x and y, times dx, the differential in x, plus the partial of y with respect to y times dy. So we can extend that to more variables if you want, and it gives us a way to approximate an increment in the dependent variable based on some incremental amounts in the independent variables. For example, if z equals pi x squared y, find the total differential dz. And we'll use this in another example shortly. By the way, z equals pi x squared y is the formula for the volume of a cylinder. You could translate that into a can if you wanted. So the partial derivative of this with respect to x, since pi and y are constants, would be just 2 pi xy. And the partial derivative, there of course times dx, the differential. And the partial derivative of this with respect to y, the pi x squared is constant, so it's plus pi x squared times dy, the differential with respect to y. So that's the total differential dz. And here's this next example will show how to use such information. Now suppose you're a manufacturer and you need cylindrical cans to be made that are 4 inches tall and a diameter of 2 inches. Then the company you deal with makes them approximately 3.98 inches tall and with a diameter of 2.03 inches. So approximate the change in the volume of the can with differentials. I mean, based on the fact that they're not coming exactly as you specified, they're coming a little bit shorter but a little bit fatter. And then we'll calculate the actual answer and compare and see how accurate our approximation is with the approximated error amount. So our function is, for the volume of a can, pi r squared h, right? And so our total differential, which is what we're going to use to approximate first, is 2 pi xy times dx, we got that up here of course, plus pi x squared dy. So let's fill in some details for that. X equals 1, you're thinking, why is x equal 1 when the diameter of the can is 2.03? You might want to pause a second to think about why that's so, but I believe you might realize, oh yeah, that x is a radius, isn't it? So you take half of that. And the y would be 4. That's how we expected the can to be, right? If the diameter is 2 inches, the radius would be 1. It's 4 inches tall, so y is just 4. The dx is 0.015. Now I'm going to give you a pause on that one and say, why would the dx be 0.15? And the answer is, well, that's half of this error amount in the radius, so that would be half of the 0.03, and that's 0.105. The dy is negative 0.02 because it's a little bit shorter, right, by 2/100ths. So filling in a few details, we'll find the total differential is 2 times pi, that's from our formula, times x, which is 1, times y, which is 4, times dx, which is 0.015, plus pi times x squared times dy, that's pi, times x, which is 1 squared, times dy, which is negative 0.02. If I do the math on this, which is any calculator will take this amount, calculate it, it comes out to approximately 0.314159, etc. You could probably see that. Actually, it looks like pi over 10. If you wanted to do a little more accurate approximation of it, that's pretty much what it looks like. So let's see, and that was an approximation, so that's pretty good that we can recognize that to be practically pi over 10. So let's see what the actual difference is by using the formula for the volume of the cylinder. Here is our cylinder as we got from the manufacturer, that's this, and here's what we expected it to be, and notice the difference is 0.315087 blah 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 blah. So the difference between this and this is about I guess that would be about 1,000th of a cubic inch. Not bad.